My name is Neil Jaitani, and today I'm going to be presenting our work, Don't Be Fooled, Label Leakage and Explanation Methods and the Importance of Their Quantitative Evaluation. This was work done with Adriel Saporta and Rajesh Ranganath. As we all know, AI is a powerful tool for delivering healthcare. In fact, AI models can outperform physicians. For example, consider using AI to detect diabetes using ECG data. Recent work has shown that AI models significantly outperform multiple experienced electrophysiologists. Because AI can accomplish tasks that humans cannot, this opens up the potential to learn something new using AI and make a scientific discovery. Continuing with our example, one such way to explain what is going on is to use feature attributions that help indicate how or which features in the input influence the prediction. However, recent notable works caution against using these explanations because they may have a whole host of problems. Therefore, before making use of an explanation, it is important to evaluate it. If we have a real-world use case for the explanation, such as they will aid physicians in diagnosing disease, then they should be evaluated directly on that task. However, oftentimes practitioners are generating explanations for more of an exploratory analysis to better understand their model or data. In this case, it makes sense to use a generic evaluation that focuses on the predictiveness or informativeness of that explanation. In this work, we base the evaluation on the approach of many others and focus on the inclusion AUC or IAUC provided by the following equation. Let's take a look at what's going on here. First, we sample some data, in this case retina fundal images. Then we use the explanation method to generate feature attributions. We then consider feature subsets of all sizes and select the top n% of features. A surrogate model trained to make predictions when features are missing then makes a prediction. Finally, the evaluation measures the log likelihood of the target variable as more of the features are included. Then the area under the curve summarizes the information. The idea is that as more information from the input is included, the better the prediction should get. If the important features are ranked correctly, the prediction should get better quickly. However, we discovered a strange phenomenon when we evaluated popular explanation methods such as Grad-CAM, SHAP, and LIME on 3 real-world medical datasets. Somehow, the methods were able to generate explanations that identified small subsets of the input that were more predictive of the target than when predicting with all the features. This is shown by the many curves that can go considerably above the red dotted line, indicating the predictive performance given all of the features. To get a sense for what's going on here, consider the following. Imagine you're a physician and you're given a note that says the patient denies chest pain but endorses abdominal pain. Based on just this info, you might think the lack of chest pain is reassuring when assessing whether or not the patient is having a heart attack. However, the presence of abdominal pain may represent an atypical presentation of a heart attack. Then you get a troponin and an EKG and diagnose the patient with a heart attack. Now you go back to the note and ask for an explanation for why the patient is having a heart attack. Instead of saying true to the patient presentation, the explanation method hallucinates and selectively selects chest pain as the explanation, which, in the absence of other information, can make heart attack appear more likely than it actually is. This is possible because popular explanation methods generate separate explanations for each class. We call these methods class-dependent methods. Most explanation methods, such as Grad-CAM, integrated gradients, LIME, and SHAP, are all class-dependent. Reiterating this, a class-dependent method would generate one explanation for heart attack and another for no heart attack, both of which can make the respective class appear more likely than they truly are. Stating this more formally, we introduce the following lemma, which states that when working with class-dependent methods that generate an explanation for the label, the predictive performance with only some of the top features can exceed the predictive performance given all of the features. This shows that these methods leak information about the true label through the feature attributions that is not captured by the input alone. To drive this point home, we conducted an experiment where we randomly permuted the labels in the dataset we were trying to explain, such that the labels were now independent of the input. We then used each of the class-dependent methods to generate explanations for the permuted labels. We found that the hallucinated explanations were able to predict the permuted label when using a model trained to predict the original labels. This suggests that class-dependent explanations can make whatever class it takes as input appear more likely. A reasonable way to fix this would be to generate explanations that consider the full distribution across classes instead of any given class. We introduce such methods as distribution-aware methods. These have two characteristics. One, these are class-independent and only use the input to generate the explanation. Two, they focus on the full data distribution by measuring the probability divergence between the distribution given all the features and that given an altered input. In our paper, we proved that because these methods are class-independent, they cannot leak the label. Interestingly, if one looks at our evaluation metric IAUC, we can consider specifying a new class-independent method that maximizes IAUC. This method can be specified as following. The first thing that is clear about this method is that it is distribution aware and measures the KL divergence between the distribution of the target given the full feature set and that given the top n features identified by the explanation method. The only problem with this method is that top n is a discrete function. Therefore, the objective requires discrete optimization techniques, such as score function gradients, which are known to be computationally expensive. Instead, we propose explanation methods that generate distribution-aware Shapley values. One, because they have a bunch of established neat properties that make them good explanations, and two, their objective is easier to optimize. Shapley values are estimated by first establishing how a given subset of features are valued. To make it distribution-aware, we propose using the KL divergence between the distribution of the target given the full feature set and that given only a subset of features. The Shapley value for a given feature is then calculated by averaging over its contribution across all feature subsets. Using this setup, we introduce two distribution-aware Shapley value estimators, SHAP-KL and its amortized counterpart, FastSHAP-KL, which follow the optimization setup by SHAP and FastSHAP respectively. Looking at the same three datasets, we see that the distribution-aware Shapley value estimators stay below the predicted performance given all the features, indicating that they do not leak the label. This is to be expected given that they generate explanations without additional information about the label. Finally, we first converted class-dependent methods to class-independent methods that cannot leak the label by selecting the explanations corresponding to the predicted class instead. We found that distribution-aware methods outperform the other methods on 2 out of 3 medical tasks, suggesting that they are a better bet when high-quality explanations are desired. Based on this, I would recommend using a distribution-aware method, such as SHAP-KL, when high-quality explanations are desired. However, ideally, multiple explanation methods should be evaluated prior to use. Interestingly, there may be use cases where class-dependent methods are desirable, such as when trying to identify the chemical moieties of a chemical compound that most suppress cancer cell proliferation. Technically, one can generate an explanation for each class in order to help explain the whole distribution across classes. However, if there are many classes, it would be cognitively difficult to make sense of the full set of explanations. Lastly, we propose a new explanation method that directly maximizes the IAUC. We believe that this would be the ideal method for the desired measure of explanation quality. However, it would require solving a computationally expensive discrete optimization problem. However, as computation cost continues to drop, this method may become more user-friendly.